Welcome to lesson 41. We're going to get into vectors now. But first, this is like a pre-game show right here. I need to talk about angles in standard position. Then we'll get to vectors. Okay, so angles in standard position. What am I talking about? Well, you see this blue line here? That one. Well, if you measure the angle from here to here, what's that look like to you? About 45 degrees? That's called standard position. Woohoo! Standard position means rotate counterclockwise from the positive x-axis. From the positive x-axis. You measure whatever angle that is. So the x-axis is kind of like your starting point. The x-axis is 0 degrees. And if you rotate, yeah, in fact, you know what? You could label this as that line is at 0 degrees and this line is at 45 degrees. That's a good way to do it. Because this angle here happens to be 45 degrees. And so we say that that line is at 45 degrees. Okay, what about this one? This one. Well, let's see now here. You're supposed to measure the angle from here all the way to here. So what would that be? Well, if you're guessing that maybe in here's about 30 degrees roughly, then we'd have 30 plus, remember right angle, this is 90 degrees, right? 30 plus 90, so this would be 120 degrees. And that's measuring the angle in what's called standard position. So again, standard position, you measure from the positive x-axis like this. So the x-axis, the positive x-axis, is at 0 degrees, and this line would be at 120 degrees. Okay, it's at the 120 degree standard position. Oh, fun game, right? Want to keep doing it? What about this one down here? Let's just agree that that's a 30 degree angle there. And if you don't think it's 30 degrees, then let's agree to disagree. No, it's a 30 degree angle. Let's just say it is. But that's not the angle in standard position. To get the angle in standard position, again, remember, you'd have to rotate from the positive x-axis. You'd have to rotate in the counterclockwise direction, like that. So what do we got there? Well, the x-axis is kind of like where you start. Call that 0 degrees. If you come straight up, that's 90 degrees. If you come all the way over this way, that's 180 degrees. Right? You've heard it said, pull a 180, which means to go exactly the other way. And then if we were agreeing that that was about 30 in there, then we've got 180 plus 30. So this would be a 210 degree angle in standard position. So this one was 45, this one was 120, this one is 210. That's a 210 angle. And then finally, what do you get to say to that one? There's actually two ways you can do this one. One way is to, buckle down and follow the definition exactly as it's stated. Start at the positive x-axis, rotate counterclockwise until you get there. Okay, so remember the x-axis is at 0. If the positive y-axis is at 90, the negative x-axis is at 180. So what's this one now? This would be 180, add another 90, you get to 270 degrees. And so where are we here? Well, notice that if I came all the way back to where I started, take 270, add 90 again, you'd get to 360 degrees. So notice 0 and 360 are actually the same direction. They're the same standard position. They're both on the positive x-axis. They point exactly due east, if you will. So if this were a 30 degree angle in there, let's just say, if this in here is a 30 degree angle, then what's this angle between here and here? This would be, since we have a 90, and that's a 30, this would have to be 60, right? Okay, so notice you've got, as you swing around, 90, 180, 270, plus another 60. So 270 plus another 60. We're talking 330 degrees is the angle in standard position. Let's make it look like a 330. There we go. That's close enough. 330 degrees. That's my standard position angle. Now, you could, I suppose, make the case that, shouldn't we just... Jeez, go away. Go away. Go away. Okay, that's a way. Good. We could make the case, and apparently I can't let my hand touch anything, but we could make the case that it would have been a lot easier to go this way. And if you want to go that way, that's fine. It's only 30 degrees, but what you're going to say is you're going to say negative 30 degrees. So sometimes we do let ourselves rotate, the opposite direction, clockwise, I guess. But you'd have to put a negative on it because that's rotating in the negative direction. So if you rotate counterclockwise, that's positive. If you rotate clockwise, that's a negative. So 330 degrees is the same thing as negative 30 degrees. Okay, so I think you got the idea now what we mean by standard position. It's measured from due east. It's measured from the positive x-axis. A positive rotation, once more, is when you go counterclockwise, when you go from the plus x-axis to the plus y-axis first. That's counterclockwise. That's the positive rotation. And if you go the other way, it's a negative rotation. Okay, so now that we got that figured out, now we can start talking about what's a vector. And I think this is the nicest way to introduce what's a vector. I think I'm in a blue mood here. Okay. So it says, you found some treasure map or something in your attic. Or maybe it's not the map, but it's got the directions. How do you get to the treasure? And it says what you got to do is, if you want to get the treasure, is you got to start at the old oak tree, and then you got to walk 8 paces east, turn north 6 more paces, and then dig. So what does that look like? Well, assuming this is where the oak tree is or whatever that you're starting, assuming that's your starting place, then you would walk 8 paces to the east. So each of these dots is meant to be a pace. 1, 2, 3, 3 paces, 4 paces, 5 paces, 6 paces, 7 paces. I have just walked 8 paces to the east. And in fact, I'm going to label that 8 paces to the east. And you know what that is? That's a vector. That is a vector. Tis a vector. What makes it a vector? Because it has a magnitude, 8 is the length, and a direction, which in this case is, you could say east, or if you want, you could say 0 degrees, right? So it's got a magnitude of 8 and a direction of 0 degrees. That's what we mean by a vector. It's a mathematical quantity. I'm trying to remember how they said it in that movie Despicable Me. It's a mathematical quantity, which is blah, 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 and magnitude. So if you didn't see that movie, you have no idea what I'm talking about. Which means you got to go watch the movie. But anyway, 8 paces east. There's a vector. Cool. Now we weren't done finding the treasure yet. That was walking 8 paces east. Now we have to turn north and go 6 more. So turn and go north 6 more and try real hard not to have my hand hit the pad and so that weird freaky things happen. Let's see, that's 1, 2, 3, 4, 5. I'd have to go here, right? 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yep. So that's walking 6 paces to the north. And of course that's another vector, right? 6 paces north. I guess maybe I'll turn and write it this way. 6 paces north. 'Tis another vector. It has a magnitude, which is 6, walk 6 steps. It has a direction, north, go north. Or if you want, you could say 90 degrees. And then dig, right? I'm going to say end. You could say dig if you like digging better. I dig putting dig there, but I also dig putting ending there. Anyway, you got to end there and dig. So, 2 vectors. Now here's the thing. Wouldn't it have been nice, instead of walking 8 paces east and 6 paces north, wouldn't it have been nice to just kind of, just kind of just walk across the lawn maybe? Like that? That's a vector, right? Now the length of that vector, we tend to use a little r to stand for how long is that vector. And here's a good question for you. How long is r? We just finished our unit on trig and solving right triangles. You can tell me how big r is, right? Of course you can. It's called Pythag. You got yourself a nice right triangle here, right? That's 90 degrees. You got an 8 on one leg, a 6 on the other leg, and so you go like this. 8 squared plus 6 squared equals the hypotenuse squared. And turns out if you solve that out, that's a 64, that's a 36. They add up to 100. You take the square root, you get 10. h equals 10, or I guess I could say r is equal to 10. So the length of that is 10. So you could have just walked 10 paces instead of 8 plus 6 is 14. Oh, you're wasting energy here. So if you cut across the line, you could have gone 10 paces. Next question. What direction is that? Let's label the direction here. Let's call that theta. What angle theta should you have walked at? Well, again, you just came from a SOHCAHTOA kind of unit, so you can say, SOHCAHTOA, I should do some kind of SOHCAHTOA. So the SOHCAHTOA that you would do would be something to the effect of, okay, here's my angle, here's my 90 degrees. Let's use the 6 and the 8. Let's just, because those are the ones we started with, right? So this would be the opposite side, right? And then this would be the adjacent side, right? Because that's the hypotenuse. So this is the adjacent. And this is opposite over adjacent. This is a TOA situation. So the tangent of that angle theta is the opposite side over the adjacent side. And remember, you have to do theta equals shift tangent now of basically 0.75. And so shift tangent of 0.75 is, did I solve this? I didn't solve this. Oh, I didn't solve this. Where's my calculator? Come on, man. I know it doesn't come out to a real nice angle. All right, I got it. You do the shift, you do the tangent, you do the 0.75 inside, you hit the equals, and you get something like 36 point, I'll just do one decimal place, 36.9 degrees is my theta. So notice that this red vector is in some sense the same as this vector added to this vector. If you walk the two blue vectors, you get to the same spot if you had just walked the one red vector. So what you've just seen here is an example of vector addition. Ain't that something? Vector addition. All right. So I think on the next page, I'm going to start giving you some official nomenclature and terminology and even formulas. So up here, I was saying this already. This is the top of page 2. I was saying vector is a quantity with both a direction and a magnitude. Represent it with an arrow because it's got how far and which way. Often the arrow is described in either rectangular or polar form. So what am I talking about here? Well, rectangular form is when you kind of do something like this. You see that 8 paces east up here? Think of that as going 8 paces in the x direction, nothing in the y direction. Notice the use of these, not quite parentheses, they're pointy, right? They're kind of like greater than, less than, except that's not what they mean. They're just pointy parentheses. You use the pointy parentheses because this is not the point 8, 0. It's go this far in the x direction, go this far in the y direction. Now, it just so happens you end up at the point 8, 0, but that's just in this case. When we walk 6 paces north, which was over here, right? How far in the x direction did we go? Well, we didn't go in the x direction. We didn't go anything in the x direction. We went purely in the y direction, right? So this is how far in the x, maybe we should notate this. How far you move in x direction, and then this number is how far you move in the y direction. Again, this is not the same thing as coordinates of points. These are lengths. Go a distance of 8 this way, go a distance of 0 this way, go a distance of 0 this way, go a distance of 6 this way. What's really nice about rectangular form is that you can add them up just by adding. 8 plus 0 is 8. 0 plus 6 is 6. Notice I said I'm adding them, right? So 8 paces east looks like that. 6 paces north looks like that. If you want to do both added together, well, you add up the two x's. 8 plus 0 is 8. You add up the two y's. 0 plus 6 is 6. And I'm going to erase that mess. But you see how it works, right? That's what I like about rectangular form. It's easy to add, very easy to add. So yeah, let's get that out of there. Let's see, go back to blue. Now there's another form which would be a lot easier if you're the guy that's, you know, shooting the artillery piece or something. Like, let's say you're the guy in charge of shooting the artillery piece, right? And in fact, you're fuchsia. So it's like, here you are with your artillery piece, and you're supposed to hit the target over there, right? Would you like it if someone said, I want you to shoot 8 paces east, turn to the north, and go 6 paces? It's like, no. Just tell me which way. That way. Okay, how far? 10, right? That's what you want to know if you want to aim your spud gun or whatever it is you've got. Turn your thingy into that direction and go a distance of 10. Boom! That's the way you get there. Anyway, that's called polar form, because if you think of the starting location as almost like think of like a flagpole or something, and you're rotating around the flagpole, right? So it's called polar form. So it's easy to say what the polar form is over here. In fact, let's do it in purple. The polar form for our ending vector is we had to go a distance of 10 in the direction of 36.9 degrees, because we figured that out, right? We did the Pythag theorem. We did the shift tangent. We knew that. And this polar form here. Come on, you. Come on, you. This polar form here. That's kind of the more, what do you want to call it, intuitive or something? Just aim your thing at a 36.9 degree angle and go a distance of 10, okay? So notice this is sort of an r/theta, like this, r/theta. R is how far you go. R is, you could think of it as standing for radius, I suppose. And then theta, of course, is direction. So, and this, by the way, is the symbol for angle from geometry class. So we just kind of put a big angle symbol like that. And we can say, yeah, go that way. Now, what do you think the polar form would have been for these two things? Rectangular form, 8 in the x direction, nothing in the y direction. Well, it looks like you're going a distance of 8, that's for sure. And you're going in the pure east along the x-axis direction. So that would be 8 at an angle of 0 degrees. That's the polar form of our 8 paces east. 6 paces north would be, well, you're going 6 paces. Which way are you going? You're going straight up, which is at the 90-degree angle. So notice the only problem with polar form, it's like, yeah, it's great. 8 at a 0-degree angle, 6 at a 90-degree angle, makes perfect sense. 10 at a 37-degree angle, makes perfect sense. But notice that you can't really say 8 plus 6 is 10. And you can't really say 0 plus 90 is 37, right? So there's the drawback to the polar form. So usually what we'll do is we'll have to, and we'll see a lot of this in the next couple of homeworks actually, is usually what we do is we take our vectors in polar form, turn them into rectangular. That way we can add up, and then we can go back to polar form like this. Again, we'll see some of that coming up in some later examples. But for now, what I should do is I should focus on this idea of how do you go back and forth? How do you convert back and forth from rectangular to polar? This one wasn't bad. You could tell, well, that's 8 east, 0 north, so it's 8 at an angle of 0. But, you know, how are you supposed to tell with this? And notice we're going to have to bring back our Pythag and our shift tangent. So here's our diagram. Let's hang our information on this diagram. Nomenclature time. So imagine this was, you know, this was the 8 east or whatever. This was like the 8 east, this was like the 6 north, and then this was the, well, we have a name for that actually. You know what we call that? We call that the resultant. We usually use a capital R to stand for the resultant. Notice the little arrow on top of the R is saying this is a vector. And the length of this arrow is little r. So we call it the resultant. R with the arrow on top is the name of this green arrow basically. And then the little r is how long it is. This of course is the angle theta. So remember, the resultant is r at angle theta. That's its polar form. Now down here, we call this the x component, because notice it's all x action. It's pure x action. The official abbreviation for that would be capital R with a little x subscript. That's the x component. And then this is the y component. I should have maybe put that word in there somehow. This is the y component, and the symbol for it is r sub y. So big R stands for the arrow. If you actually draw the arrow on top of it, you're referring to both the r and the theta at the same time. For the components, we don't put the arrow on top of it. We go r sub x, which means the x component, r sub y, which means the y component. Little r, again, what did you just do? Little r, again, is the length of the arrow. Theta is the direction. In standard position, which is why I had to tell you about that standard position stuff, theta is in standard position because it's possible you'll have vectors that are pointing that way. And so the theta might be 120 degrees or something. Okay, so theta is in standard position. That's important. Now formulas. Maybe I'll do the formulas in a lighter green. You need to keep these handy. You're going to need these formulas. The formulas are for converting back and forth. Now, we already saw two of these without even knowing that they were formulas. The length of r is called r, right? Little r. And we already saw up here how we got that. We got this length of this arrow by doing a Pythag theorem. We took what's the x component here and squared it. We took what's the y component and squared it. We added them up, and then we had to take a square root. So let me try to clear up some of this mess. That's what we're going to do. Take the x component squared. Take the y component squared. Oops, what am I using v's for? R's. Take the x component squared. Take the y component squared. Add them up, and then take the square root. Big, big formula. That's how you find the r. That's how you find the length of a vector. Given its two components, you know the x component, you know the y component, you can get the r that way. And then you can get the angle, theta. Remember what we did? We did a shift tangent. It's the y component over the x component because we did a shift tangent of this, right? The tangent of theta is opposite over adjacent, so we had to do a shift tangent of those two, ry over rx. So those two formulas get you the r and the theta. What if you had the r and the theta and you wanted the rx? Well, here's formula 3. The x component is, and if you do more SOHCAHTOA, you can prove this to yourself, but I'll just give it to you. You take the r times the cosine of that theta, and ry is you take the little r times the sine of that theta. Okay? Those are your big formulas. Huge, massive, unbelievably important formulas that should be highlighted. Maybe you should highlight your formulas. Get out the crayons or something. Magic markers. Do they call them magic markers anymore? I bet you they don't. I know. Cut them out with scissors. Glue it on your something. Glue it on your rear view mirror. No, that's bad. Glue it on your windshield. That's bad. Glue it on your refrigerator. Glue it on something that you go to every day. Something. Anyway, those are the 4 formulas we're going to need. Those formulas let us convert back and forth. So now let's do examples where we convert back and forth. Now in the homework, I'm going to have you practice using these formulas, and I'm also going to ask you, if you read the instructions to the homework carefully, it's going to say, draw the picture to show what's going on behind the formula, what's going on behind the scenes. So I'm going to follow that habit here. I'm going to use the formulas, of course, but I'm going to draw the picture too. So the picture is, Biff walks 12 east, turns 5 south. Okay, so I have to go something like this. 12 east, turn 5 south. So that's kind of the basic idea. Bonnie starts at the same spot but wants to take the direct route, so what r and theta should she use? So notice this is a vector addition. She's cutting across the lawn, right? And then the question is, what's the r and what's the theta? Well, that's the same thing as this situation up here. The triangle's upside down, but other than that, it's the same situation. Basically, think of this as the r sub x and think of this as the r sub y. And what we're going to do is we're going to get the r and the theta. So the r, now the formula says square root of rx squared plus ry squared. But you can see what the formula is doing. It's just doing a Pythag theorem. The 12 squared plus the 5 squared, add them up, take the square root, you get this. And it turns out, if you plug in 12 squared plus 5 squared, add them up, square root, you end up with, I want to say 13. R is exactly 13. I'm pretty sure that's right. Yeah, that's right. What's the theta? Well, you got to do the shift tangent of the y over the x. Ooh, sneaky. Notice the y component. Well, let me write ry over rx first of all. But notice the y component is negative. That's going down 5 to the right 12. I think that's worth highlighting in red. Okay, this is actually, if you think about it, I probably should have, it says 5 paces south, so it's okay to put a 5 and show that the arrow is going south. But it's not quite right to say equals ry. I probably should have done something like this. ry equals negative 5. That's what I should have done. Rx is equal to positive 12. Ry is equal to negative 5. Now it makes sense. And by the way, back in this Pythag formula, you would have had a negative 5 being squared. Notice it doesn't really matter. If you take a negative 5 and square it, it's still a positive 25. So whether you entered it as a negative or a positive didn't really matter for the Pythag theorem. But it matters a whole lot for the shift tangent. So if you do the shift tangent of negative 5 over 12 with a calculator, okay, shift tangent negative 5 over 12 is. Notice the calculator gives you a negative angle, negative 22.6 degrees. So the calculator knows, hey, you had to rotate clockwise, not counterclockwise. Remember, counterclockwise is a positive rotation. You rotate this way, that's a negative rotation. And the calculator knows. Well, it knows as long as you plug in the negative 5 for your y component, 12 for your x component. All right, what do we got over here? Example 2. Cliff walks 8 to the west, turns 15 north. Okay, so let me try to draw this carefully. 8 to the west. So since it's to the west, notice it's in the negative x direction. So I'm going to say that the x component is a negative 8. So I can use a positive 8 here because the 8 is labeling an arrow that's going in the negative direction. But as far as plugging into formulas, I should use r sub x equals negative 8. So then he turns, and it looks like I've got this way not to scale. Wink. And then he turns and he goes 15 paces to the north, something like, even better, even higher than that. 15 paces to the north. Now that's going up. So the y component really is positive. The y component is a positive 15. Clara starts at the same spot that Biffy did, or Cliffy did, but she walks across the lawn or whatever. She goes up to here. This is Clara. What r and theta should she use? So r is how far, and theta is, whoa, look what I almost did wrong. Huh? Look at that. Theta should be in standard position, which is over here, from the positive x-axis. So that's the y-axis, kind of. That's the x-axis, kind of. Okay. That would actually be the theta in standard position. Now, fortunately, the formulas are going to take care of all this stuff as long as we use the formulas as specified. So r equals square root of, you take the x component squared, take the y component squared, and you plug in the x component is negative 8. But notice, again, if you're putting it in parentheses. By the way, you have to do that. Let me take a second and just warn you. So I'm going to erase this in a minute. So if you need to write this down. If you type the negative button on your calculator and then the 8 and then the square button on your calculator, you know what it's going to tell you? It's going to tell you negative 64. And then you should draw somebody with the hair coming way out like this. Negative 64, that's not what I mean. Because what you mean here is you need positive 64. Okay, and so let's get this distracting stuff out of the way. That's enough of that childish stuff. So must either type it in parentheses, use the parenthesis button, and then square it. That way you're sure to square the -8. See, here it's not squaring -8. It's only, the square button is only squaring the 8. It did not square the negative. If you want to square the negative, you have to group it with the 8 in parentheses. And then when you square it, then it'll give you a positive 64. Okay? So you must either use parentheses or skip the negative, which is a dangerous thing to say. But if you're using this Pythag formula, it's fine, right? It's going to be positive whether you square an 8 or whether you square a -8 inside parentheses. It's going to come out to positive 64. So personally, I just tend to skip the whole parentheses thing. I just ignore the negatives when I'm using the Pythag theorem. That's what I do. All right, so now I have to get rid of this. So I hope I made that point. Be very careful about that. So when I'm writing down the formulas, I'm going to, because I am plugging in a -8, I'm going to have to show it in parentheses. And again, like I say, don't skip those parentheses. If you're going to type the negative in, don't skip those parentheses or your answer will be so wrong. So wrong. And then when you get it wrong, I'll have to either remind you or I'll have to say, hey, watch the videos. Well, yeah, geez, they're here for a reason. Getting back to where I was, which was where? Here. Where were we? We're trying to get R. We put in the Rx and we squared it. Now we have to add and put the Ry in. The Ry is a positive 15. No problems there. And I do believe this comes out to exactly 17. I'm almost positive. To get the theta, you have to do shift tangent and you have to do the y over the x. Some people get that backwards sometimes. Make sure. Come back up to this formula for a second. Make sure you do y over x, okay? Y over x. It's kind of like if you've ever played with the slope formula in an algebra class where I always say they always say change in y over change in x, y over x, y over x. It's kind of like a slope we're plugging in, so y over x. Anyway, the y component is a positive 15, and the x component, the sign is important here, very important. So if I hit shift tangent, and I put a 15 over a -8, this is telling me that the angle is -61 point, let's just call it 9 degrees. Now in the day version of this class, I always like to stand there for a few minutes and see if anyone notices that there's something horribly wrong here. Have you noticed that there's something horribly wrong with that answer? We've done everything correctly. We plugged in the positive 15, we plugged in the -8, we put the y on top, the x on the bottom, we hit the shift tangent, we're in degree mode, everything's good. Why is the calculator giving us -61.9 degrees? Because this is not a negative angle. Well, sometimes calculators needs to be fixed, or the calculator's answer needs to be fixed. I don't really like the way that looks. Let's get that out of here. Let's put it this way. When doing shift tangent, there's always two answers. But calculator gives you one of them. In other words, there are two angles that have a tangent of 15 over -8. There's this angle, that's a -15 over 8, and then there's this angle, that's also a -15 over 8. So there's two angles, there's this one and there's this one. And the calculator can't tell the difference between the two. So the calculator either gives you the right answer or it gives you exactly the wrong answer. So let's write that down. Sometimes you have to add 180 to what the calculator says. So the calculator is trying to tell us negative 61.9 degrees. But then you look at this and you say, that's the wrong way. No, the other way, the other way. And so you have to fix it. You have to add 180 to get, what is that? Shame on me. I'm pulling out my calculator. Shouldn't know how to do that. But I did. So you're getting a 118.1 degrees. That's the true. That's what this is. This is a 118.1 degrees right there. Okay, it's not negative 61.9. No, it ain't. You have to add 180 to it to fix it. So important example, right? So maybe when where we wrote the formulas up here, maybe we should put a little star here and say, sometimes you have to add 180 to the answer. How do you know when? Well, I could give you a rule, but what I'd rather have you do is just draw the vector and do it that way and say, well, my vector is supposed to be going this way. So if they're giving me an angle that goes this way, that's how I know that it's wrong. That's really the best way to do these things. Memorizing a rule is like, what's a rule? How are you going to remember a rule? But if you develop a habit of drawing pictures and looking at the pictures and saying, well, that can't be right. That's obviously not right. Not only is it healthier, but you'll be more sure of yourself than if you say, I think I'm remembering the rule right. What a terrible position to be in. What's the rule? I think the rule goes like this. Well, how do you know if that's the rule? Well, the way to test it would be to draw it in the first place. Just draw it, right? Just draw it, and then you can convince yourself what you're supposed to do. So keep an eye out is what I'm saying. Whenever you hit the shift tangent button, keep an eye out. Okay, so examples 1 and 2 were basically when we had the x and y components, we put it together to get the r and the theta. Now we're going to go the other way. We're going to say, hey, I've got the r and the theta. Let's figure out what the x and y components are. Now this is actually going to be an easier game to play. So it says here, the vectors below all have a length of 100. So I kind of forgot to put that in there. So it's 100, okay? To break it into an x and y component is kind of like that treasure map thing. Instead of cutting across the lawn, you stay on the sidewalks, sort of. So if you drop a plumb bob to the x-axis, always to the x-axis, never to the y-axis, always to the x-axis. So wherever your arrow is pointing there, drop a plumb bob to the x-axis. Then you can say, well, the shadow here on the x-axis, that's my x component. And this vertical part over here, that's my y component. And we could do SOHCAHTOA, but we don't have to because these formulas are so nifty. Rx is equal to r cosine theta, Ry is equal to r sine theta. You can see those on page 2. R, of course, is the length of the vector. Times the cosine of the angle. Just make sure you're using the angle in standard position. Maybe I'll write that as a note. Or maybe I'll use the note over here. Use theta in standard position. But this angle that they showed us, that's in standard position, right? It rotates counterclockwise from the x-axis. So we're good. We're all good. So 100 cosine 60 is, I want to say that's exactly 50. And then our sine theta would be 100 times the sine of 60 degrees, and I want to say that's 86.6. Just because I've done this so many times. Okay, let's see if I can, let's just double check. 100 cosine 60, I'm in degree mode. Yep, 50, perfect. 100 sine of 60, I'm in degree mode. 86.6. Yep. That's good. That's good. So that's all you guys to do. So the only thing you have to really be careful of with these formulas is make sure you're using theta in standard position. Next. Okay. Again, we're saying that the R is 100 for all of these examples, so I'll just write that on there. Drop a plumb bob, or in this case, lift a plumb bob, I guess. Drop a plumb bob from the x-axis, I guess, right? So this part here that goes along the x-axis, that would be the x component. And this part here that goes straight down, that would be the y component. So again, it's like taking our, walking across the lawn and turning it into walking along the sidewalks. So Rx this way, Ry this way. Okay, cool. We have such nifty formulas for these. Rx is always equal to R cosine theta no matter what. Ry is always equal to R sine theta no matter what. The important thing is to get the theta right. So the theta here, don't be going too fast. Don't be just grabbing 20. Don't be just grabbing 20. Because this is in the negative rotation sense, right? So really theta is negative 20 degrees. It's in the negative rotation sense. So I come up back over here and I say, okay, so the R is 100 and I'm doing the cosine of a negative 20 degrees. Here the R is 100 and I'm doing the sine of negative 20 degrees. And let's see what we get here. So if I say 100 cosine of a negative 20 and I close my parentheses, it's telling me, well, 93.97 if I go to 2 decimal places. And then here we got 100 sine of a negative 20 is. And here's the cool thing. It's telling me that I have a negative y component, negative 34.20. And ain't that the truth, huh? That's a negative y component if I ever saw one. It's going down, and so the y component is negative. Woo-hoo! So if you had just put 20 in instead of negative 20, you would have got a positive 34 instead of negative 34. So it's a kind of a small point, really. But if you're careful about always using your standard position angles, then the components will always come out exactly right. And sometimes if you don't, sometimes it'll be off by more than just a sign. So I think it's a good idea too. So it's the last example. This is the end of the lecture after this one, folks. So again, we're saying that the little r is 100 for this whole page. Plumb bob from the x-axis, always from the x-axis. So this shadow along the x-axis, that's my x component. And then this part that goes straight down, that's my y component. Okay, so formulas. X component is always and forever r cosine theta. Y component is always and forever r sine theta. The trick is using the right theta. That's the trick. So let's think about this then. Supposedly, we're supposed to use the angle going in the counterclockwise direction from the x-axis. This is theta in standard position. Or if you want to rotate this way, that's fine. Just make sure you put the negative in front, right? Because that would be in the negative direction. It's probably easier to use the negative direction because here's 90. 90 plus 30, so it's 120. So I'm going to put negative 120 degrees in here. Now let's see what happens when we push these here buttons. 100 cosine, negative 120 degrees mode, right? Great. Equals, oh, it says negative 50. X component of negative 50. And then what do we got here? 100 sine of negative 120. SD button, negative 86.6. So notice it gave us the negatives for both components, which is cool because it just so happens this x component is in the negative x direction, right? You start at the origin, you go that way. And the y component also goes down in the negative direction. So by making sure that you use the angle in standard position, you will also make sure, that will ensure that you get the right signs, S-I-G-N-S, on your components. By the way, you could have put in, let's see, if this is 30, if this is 30, then this would be 60, 180 plus 60. You could have used 240 instead. And I invite you to just, if you plug 240 in here, a positive 240 in here, you'll get exactly the same answers. the math always knows what's going on. As long as you plug in the right numbers, it knows what's going on. Okay, cool. So that's our nice introduction to vectors. So what's the take-home point really comes down to like this diagram right here. The old, you can think in terms of components along sidewalks, along the x direction, along the y direction, and then you add those up to get a resultant, which has a diagonal length and an angle. Or you can take one that has a diagonal length at an angle, and you can drop a plumb bob to the x-axis and get yourself an x and a y component. So practicing going back and forth for now is the main idea of this problem set that you're about to do.